7.2, we're going to talk about log functions and their graphs. So yesterday we did exponential functions. Today we're going to do logs. Log functions and exponential functions are inverses of each other. It's like addition and subtraction are inverses of each other. They're opposites. With our log functions, we read it as log base A of x. That's how this would be read, as log base A of x. That little number below is our base. Again, you guys have seen logs 100 times, so you should know this. It's just a review of logs. We can write logs in exponential form and exponential functions in log form. So we're going to be going back and forth from log to exponential, exponential to log. So like I said, they're inverses of each other. A lot of times, if we're not given a calculator, we can't really compute logs in our head like we could exponential equations, where we could just plug in the number, figure out what our exponent is. It's a little bit harder to do that with log functions. But one way that we could graph them or plot points is we can find what our exponential function is and then switch the x's and y's. So like I said, they're inverses of each other. The y's become the x's in a log function, and the x's become y's. So if I had the point, this point would be 0, 1. Then on my log function, the inverse of it, we would have the point 1, 0. So that works with every point. So you could just graph your exponential function and then switch the x's and y's, and that would be your graph for the log function. So we're going to be rewriting from log form to exponential and exponential to log. We always start with the base. So our base is b. The number that it's equal to becomes our exponent. And then what we're taking the log of would be what it's equal to. So the other two numbers kind of switch positions. If I had, let's say, log base 2 of 5 is equal to x, I would start with the base. So I start with 2 to the power of x is equal to 5. So here I have 2 to the power of 3 is equal to 8. So log base 2 of 8 is equal to 3. On the next page, we're evaluating our logs for example 1. So it gives us what x is equal to. I don't know why it just didn't plug it in the start. But here we're finding log base 2 of 32. So like I said, our brain doesn't really compute logs, but we do know how to compute exponents. So let's change this into exponential form to solve. So I'm going to say 2 to the power of, we'll call it y, I'll call f of x y just to make it a little bit easier, is equal to 32. So we want to think 2 to what power gives us 32? Five. Perfect. All right, so let's do that for b. We're going to plug in 1 into the x. When we rewrite this into exponential form, we have 3 to the power of y is equal to 1. 3 to what power would give us 1? 0. Awesome. So y would equal 0. Let's do it for c. So I'm going to plug in 2. So we have 4 to the power of y is equal to 2. 4 to what power would give us 2? 1/2. Awesome. So y would equal 1/2. And then let's do d. We're going to plug in 1 over 100 into the x. So I have 10 to the power of y is equal to 1 over 100. 10 to what power would give us 1/100th? -2. Awesome. A negative exponent turns it into a fraction. So y would equal -2. Perfect. Good job. Next, we have properties of logs. You've seen these before. Anytime we take the log of 1, it gives us 0. It's because whatever our base is to the power of 0 would be 1. So we could just solve this by putting it into exponential form. If I had log base A of A, if these are the same numbers, then that would be equal to 1. Similar to that, if we had log base A of A to the power of X, log base A of A cancels each other out, so we would just be left with X. And then if we have a log is equal to a log with the same base, the logs just cancel each other out, and we would say X is equal to Y. Whatever we were taking the logs of, we just set them equal to each other. So for A, we want to solve the equation. If we have a log is equal to a log, we said we can just cross off the logs. So what would X equal here? 3. Log base 4 of 4, we said was equal to what? If we have the same base. 1, awesome. So this would cancel, we'd just be left with 1 is equal to X. In C and D, we're just simplifying. So log base 5 of 5 to the power of X would simplify to what? Just X, awesome. And then in D, we have 6 to the power of log base 6 of 20. What would this simplify to? What do you think? So 6 to the power of log base 6 would cancel. We're just left with 20. So next we're going to sketch a log graph. So we're going to go to example 3. It says in the same coordinate plane, sketch the graph of each function. So I'm going to start by sketching the graph of 2 to the power of x. This is the exponential version of log base 2 of x. So we're going to start by making a table. Just like we did when we graphed our exponential functions yesterday, I'm going to plug in a few values. So I'm going to plug in, we'll plug in -2, -1, 0, 1, and 2. So we're plugging that into 2 to the power of x. So when we plug in -2, we have 2 to the power of -2, which would be what? 1/4. When we plug in -1, we have 2 to the power of -1, which would be 1/2. Then 2 to the power of 0 is 1, bless you, 2 to the power of 1, 2, and 2 to the power of 2, 4. Perfect. So let's graph these points. So I start with -2, 1/4. So I'm going to go to the left, -2, and up 1/4. Then -1, 1/2. So go to the left, -1, up 1/2. 0, 1, stay at 0, go up 1. 1, 2, the right one, up 2. And then 2, 4. We're going to go up 4. There. So our graph looks like this. This is our exponential function. We graphed these yesterday. Now for our log graph, we're just going to switch the x's and y's. So instead of having a point -2, 1/4, we're going to switch them. This would be 1/4, -2. The next point would be 1/2, -1. The next point would be 1, 0. Then 2, 1. Then 4, 2. So we just found the inverse of each of our points, and we're going to graph these now. So I'm going to go to the right 1/4 and down to -2. Then I'm going to go to the right 1/2 down to -1. Then to the right 1, stay at 0. To the right 2, up 1. And then to the right 4, up 2. So this would be our log graph. It graphs it for us on the next page, so this is just the solution to the last one. Here's our characteristics of log functions. So it says the x-intercept is 1 and there is no y-intercept. This will change if our function moves or if we have a shift in it, if we're adding or subtracting something. So our x-intercept isn't always 1, but to find the x-intercept, we would plug in 0 for y. The y-axis, or x is equal to 0, is a vertical asymptote. This will change if we have a shift. So if, let's say, we had log base b of x plus 5. Whatever's in our parentheses here is going to be our vertical asymptote. So I would say the vertical asymptote is x plus 5 is equal to 0. We just set it equal to 0 and solve. So subtract 5, we would get x is equal to negative 5. This would be our vertical asymptote. So whatever's in the parentheses, set it equal to 0 and solve. That's your vertical asymptote. The domain here is not all real numbers because we have a vertical asymptote if our function is going to the right. So like a normal log, if we don't have any reflections on the y-axis here, then our domain would be from 0 to infinity. That'll change if we have a shift. It's wherever our vertical asymptote is to infinity. If our graph flips on the y-axis and now goes to negative infinity, it would be negative infinity to whatever our vertical asymptote is. And then it says if b is greater than 1, our function is going to be increasing, like the picture on the left here. This is our increasing log. And then if b is in between 0 and 1, if it's going to be a fraction or a decimal, then it is decreasing. So it would look like this. All right, next we're going to talk about the natural logs. So ln is our natural log. ln and e are inverses of each other. So ln comes from log base e. So that is our natural logarithmic function. In example 4, it just wants us to use a calculator to find the function. So we would take the ln of 2. You can plug this into your calculator. I have faith that you guys can do these on your own. Last page, it wants us to find the domain of each function. So here we have the ln of x minus 2. Our log rules, when we did our log graphs, apply to these two. So to find our domain, we set whatever's in the parenthesis equal to 0. So we have x minus 2 equals 0. So x is equal to 2. Our ln graph is going to have the same shape as a log graph, so it'll look like this. But it starts at the vertical asymptote, which is going to be x is equal to 2. So our domain here would be from 2 to infinity. We're going to do the same thing for b. We set whatever's in the parentheses equal to 0. So 2 minus x equals 0. We get x is equal to 2. Now here we have to be careful because we have a negative x. Which way does that shift, or what type of transformation do we have here? If we multiply by a negative directly to the x, it is a reflection on which axis? The y-axis. So instead of our graph looking like it did in A, where it goes to the right, we're going to flip it on the y-axis. So now it's going to look like this, where our vertical asymptote is at x is equal to 2. So from here, our domain is going to be from negative infinity to 2 because it's going to the left. So our x values now go to negative infinity. C is super funky. We have the ln of x squared. Our graph actually looks like this. Where if we set x squared equal to 0, we would get x is equal to 0. So our vertical asymptote would be at x is equal to 0. What do you think our domain of this graph would be? So they don't quite touch. It would be at 0. Because our vertical asymptote would be at 0. So it'd be from negative infinity to 0, and then from 0 to infinity. The last page is just the graphs of each one of those.